Oh, hi, everybody. Welcome back. Um, Today, we're going to continue with the reaction of bromine with an alkene. But now, instead of just bromine, the solvent will be added will be water. Now, remember, let's backtrack a second. When the only reagent is bromine, there's no water. So when you just have bromine, then what happens, of course, the pi bond breaks and we get two new sigma bonds to two bromine atoms, right? You form a dibromide. You can do the same thing with chlorine and form a dichloride. But when you add water, you get a different product. See, in this case, the pi bond still breaks and you form a bond first to one bromine atom and then the other bond is to an OH group. The OH, of course, is derived from the water. And this type of compound with a Br and an OH on adjacent carbons is called a halohydron or a bromohydron. And you can do it with chlorine too. The mechanism, the way this takes place is down here. The bromine first reacts with the double bond in the same way we showed last time. The pi bond, there's a nucleophilic attack on the bromine. The BBr bromine bond breaks, and one of the lone pairs on the bromine forms a bond to the other vinyl carbon. So the result is that you form this cyclic intermediate, three-membered ring intermediate called a bromonium ion. Okay, now that's formed in the reaction with just bromine and in the reaction bromine in the presence of water. Now when water is present, the water undergoes a nucleophilic attack on this carbon. Notice it always attacks the more substituted carbon, the carbon with the greater number of bonds to carbon. And I'm going to explain why later. And then the CBr bond breaks, the three-membered ring opens, and you end up over here with the water attached again to the more substituted carbon. A second water molecule will come in and remove the H from the protonated water, giving you the final product of bromohydrin. So that's the mechanism of that reaction. So I'll explain now why the nucleophile, the water, attacks the more substituted carbon, right? So you have to look at the transition state. So in this transition state over here, the bromine is attacking the more substituted carbon. Now, it's believed in the transition state for these reactions, because the three-membered ring here, because this three-membered ring is very strained, there's a lot of angle strain, it's believed that that bond in the transition state is extensively broken. It's broken to a very great extent. As that bond breaks, positive charge develops here. Now, the nucleophile comes in, provides electrons, and that would neutralize the positive charge, but it's believed that very little bond formation has taken place with the nucleophile in the transition state. Excuse me. Okay. So what happens, you have this exploded transition state with positive charge at the carbon. Okay. So when the attack of the nucleophile is at the more substituted carbon, you have a positive carbon on a tertiary carbon. It's a tertiary carbon. Over here, look at the transition state over here where the nucleophile is attacking the less substituted carbon. Then the positive charge develops here. And we can call that a primary carbon, right? So we have a positive charge on a primary carbon when the nucleophile attacks the less substituted carbon, and a positive charge on the carbon when it attacks on the tertiary carbon when it attacks a more substituted carbon. And so, we know that tertiary carbocations are more stable than primary. So this transition state over here is more stable, right? And so the barriers would look kind of like this, where this would be the transition state for attack at the more substituted, carbon, and this would be the transition state for attack at the less substituted carbon. You see the much faster reaction attacking the more substituted carbon because the positive charge is better stabilized at the tertiary position. Okay. Okay, so here's a few reactions just to practice with. We're going to just write the products of these reactions. So in the first one, the pi bond breaks. The water is going to end up on the more substituted position, right? So why did we show the stereochemistry here? Well, we did because this is a chiral carbon. And here we're showing the water coming from the front of the molecule, from the top of the molecule, where this chiral carbon would have the R configuration. But remember, because the starting alkene is optically inactive, it's achiral, and the reagents are optically inactive, they're achiral, the products must also be optically inactive, right? You cannot generate optical activity from reagents that are optically inactive. So the only way, as we've emphasized previously, that a chiral molecule can be optically inactive is if it's formed as a racemic mixture. So that's exactly what happens. You form a racemic mixture, 50% of the R bromohydrin and 50% of the S bromohydrin. Okay? That's why both products are shown. Okay? So let's look at the next example. And in the second example, the same reaction, the OH is going to attack at the more substituted position. And there you go. And you see forming a pair of enantiomers. Let's analyze it. Let's analyze this structure. So in this case, notice the OH of the water ended up attached to the more substituted carbon. In this case, the bromine came in from the top. And you notice the OH came in from the water, came in from the bottom. So this is characteristic of these reactions. They proceed with anti-addition, just like the bromination, which we talked about previously. The bromonium ion is the nucleophile comes in from the back side because it is an SN2 type reaction. And again, because we have chiral centers here, we actually have two. We're going to get a racemic mixture, and the enantiomer of this is this over here, where the initial bromine attack is from the backside. That means the water will come in from the top. So the OH and the bromine will always be trans to one another. And this is the particular pair of enantiomers that you end up with, okay? And finally, in the last example, we're starting out with a cis alkene. These carbons are equally substituted. Just one carbon group attached to each, so there's no preference which carbon the bromine or the water end up with. But the stereochemistry is relevant. And as you see here, what happens, the bromine in this case comes in from the front, then the OH and the water will come in from the back, right? And then this has two chiral centers. We're going to also get the enantiomer. You're going to end up, of course, with an optically inactive racemic mixture.